All right, so you've got your printout from 2.6 in front of you, so you can see at the top what our topic for the day is. We are going to talk about the operations on functions, of which there are 5. And the first 4 we're going to talk about are going to be very familiar to you. They are the things that you have seen as you've done algebra in a number of contexts, and we're going to go through some examples. So at the top of the page, it says operations on functions. If I give you 2 functions, f and g, those are the letters that we are using because that's what the book uses. For all values of x, for which both f of x and g of x are defined, meaning any values of x that are in the domains of both functions, we can define the first 4 operations. The first operation is called function addition. I don't think this is going to be too astounding. It's just a notational thing, and then we're going to apply it. But if you have f plus g, this is the addition function. Then if I want to add 2 functions, what I can do is I can then separate them, and I can consider the 2 functions as separate entities and add them together to get the addition function. So what this says is that whatever x value we're at, we can find the function value at the function value of f at that x value, the function value of g at that x value. When we add them together, we get the addition function's value at that x value. So for instance, example 1. Example 1 gives us these 2 functions. F of x is equal to the absolute value of 2x plus 1. G of x is equal to x squared. And so in example 1, the thing that I've asked you to find is f plus g of 2. So this new composite function, whatever it would look like, okay, whatever that, and we'll talk about what to do with this in general terms in a minute, but this new composite function, how do I figure out this value at 2? Well, what I'm going to do, and for the first couple, we're going to write out our steps just so that when you're looking at your notes later, yeah. Where'd I get what from? This is the problem. Okay, so these are the functions that I've defined, and this is what we're going to evaluate right here. This is I've given to you. So what we're going to do then is we're going to separate this into my individual functions, and we're going to say, okay, here's the function f. We're going to find its value at 2. We're going to add that to the function g's value at 2. So I'm just considering the component parts. Hopefully this part doesn't strain you too much. We've talked about function notation. This is not necessarily too new. I'm going to put 2 into the function f. And when I put 2 in, 2 times 2 is 4. 4 plus 1 is 5. Absolute value of 5 is 5. Plus g of 2. When I put 2 into the function g, 2 squared, 2 times 2 is 4. So the addition function, the output we get from the addition function is 9. And there we go. What I would like you to do is exercise 1 that's just right to the side. It says, what's f plus g at the value -5? You are just now going through the motions that I just went through. We're using the same functions, by the way. F plus g at -5 is going to be whatever I get at the function f at -5 plus the function g at -5. Again, I'm just going to plug those values in. This is the arithmetic part of it. So when I put -5 in, 2 times -5 is -10. -10 plus 1 is -9. Absolute value of that is 9. And then when I put -5 into g, when I plug -5 in here, -5 squared, -5 times -5 is 25. Great. Because the negative is the value that we put in, we square the negative in that case. Okay, we do not leave that outside. So -5 times -5 gives me 25. So this answer ends up being 34. And that is function addition. So next, on my operations on functions. We can then talk about, if you go back up, you see I've begun the definition of the first four operations, function subtraction. So what is the difference function? F minus g of x. Well, again, all this is significant mathematically. It might not appear significant to you as I'm presenting it to you, but all this is saying is that there's no reason when I'm considering the difference function that I can't break it into its separate parts. There's no mysterious thing that I have to take into account. It's kind of like when you want to square, like if you want to square x plus y, it would be nice if we could just go, oh, that's x squared plus y squared and be done with it. But we have to FOIL and you get that middle term. And this is saying there's nothing that you're not observing or nothing that you're just not knowing by instinct here. So the difference function goes like this. It's the same thing. I don't think I'm going to, again, put anything mysterious. I'm going to take the function f of x, and I'm going to subtract the function g of x. So if you would do this for me, make your best effort at exercise 2. Do the difference function. We're still working with these two functions right here. Do the difference function at the value 8. All right, here goes. I'm going to take f minus g of 8, and I'm going to break it into its parts. I've got the function value of f at 8 minus the function value of g at 8. So when I plug 8 in, 2 times 8 is 16. 16 plus 1 is 17. Absolute value gives me 17. This time it's function subtraction. And so g of 8, 8 squared, 8 times 8 is 64. And 17 minus 64, is that negative 47? All right, excellent. I did arithmetic in my head while talking. That never usually goes well, but today is an anomaly, I guess. We doing okay so far? Yes, sir. Do we have to put the Fourier lines like on the test or whatever? You're not. This is not a solution. This is an output. So no, we're not. This is not a solution set. This is f minus g of 8 is equal to negative 47. So that's a great question. It's a notational question. We're not solving an equation, so there's no solution set here. The next one on your sheet is function multiplication, f times g of x. And lo and behold, I think you could probably all have already written this down. It's just going to be the function value of f at x times the function value of g at x. After you've written that down in our definition up above, go ahead and do exercise 3 with these same two functions. Find f times g evaluated at 4. So I'm going to do my function multiplication, f of 4 times g, that's a mess, times g of 4. F of 4, 2 times 4 is 8, plus 1 is 9, absolute value is 9. G of 4, 4 times 4 is 16, and 9 times 16 is something like 144. One more basic operation. Again, I didn't think these, and if you have a question, I'm not saying don't ask questions, don't be embarrassed, but my expectation, if you're like most classes that I have, is this is not too staggering of a thing to behold. But if you do have a question, let's get it out there so that we can all feel good about this. The last one is the quotient function, f divided by g of x. And again, as you would expect, that is just the ratio of the function f over the function g. But there is one caveat on this one that is not present in the others. We always want to be conscious of our domain. And when we divide things, and we're going to talk about this in more detail, and I think it's the 4th unit of this class when we talk about rational functions. But for now, just remember that this is true for all x's, for all x values in which g of x is not 0. And that's just a complicated way to say that you avoid the x values that are going to make a denominator, are going to make an output that's 0. So as you're going through your homework, and we'll probably do it in here, you might be asked to find the quotient function, but then you also, after that, might be asked, what's the domain of the quotient function? So you'll have to make sure that anything that would make the denominator 0 is now excluded from our inputs. So if you would do me a favor, this is not a trick question. If you do exercise 4 and find the quotient function of our f and g, this is the last example with them. We're going to retire them. If you would find that evaluated at 2. So a lot of you are looking at me, which makes me uncomfortable, so I'm going to get started with this. So we have f evaluated at 2 in the numerator, and then g evaluated at 2 in the denominator. So I'm just splitting it apart. 2 is a perfectly legitimate thing for the domain. In fact, suggest to me, we'll do this in a minute when we're talking about general functions, what is the input, what's the x value that is in the domain of both of these, but is not in the domain of the quotient? What x value? What would make this function have an output of 0? Yeah, the x value 0 would give me an output of 0, so we would have to exclude that. It's undefined for this particular problem. Okay, so f of 2, 2 times 2 is 4, 4 plus 1 is 5, absolute value of 5 is 5, 2 squared is 4, and there you go. That's my output, 5/4, or if you feel like extra work, 1.25. All right, so that is the 4 basic operations. Yes?
So does it matter if we switch it to a decimal or a fraction?
I am fine with a decimal as long as it's a terminating decimal. If this was like 5/3, I'd want it left 5/3. Okay. All right, so if you would, when you're an engineer or when you're in chemistry class, you round. When you're in math, we like exact answers. Mathematicians are uppity that way. So the next one, example 2, and exercise 5, and exercise 6. Oh, hang on, no, I'm sorry, I'm leading you astray. That's all I have for particular values. Are we good up till now? All right, well, now I'm going to change the functions, and we're going to talk about constructing the general function. So for instance, if f of x is x squared plus 5x and g of x is 2x minus 7, those are my 2 functions. Now what I want to do is, instead of thinking about a particular value, I want to know what is the equation for all values that would give me the addition of these 2 functions. So what equation could I graph that represents the addition of these 2 things? Okay, well, that's not going to, again, be too difficult to figure out. I'm going to take f of x, and I'm going to add it to g of x. So in this case, again, we're not talking about a particular value. I'm going to take f of x. What is f of x? What am I going to put here? Yes. And then what's g of x? What am I going to put right here? Excellent. And then the only thing you have to do is, in the event that there's any operation you can do, like we have like terms here, or if there's anything you can multiply together, then go for it. And so I'm going to add those like terms. So x squared 5x and 2x is 7x minus 7. So when we can graph parabolas like this, we'll talk about that. That's the next unit. When we come back next week, we begin talking about that. We could graph this and we could graph this line both on the same axes and look at them. And then if we graphed this parabola would represent value for value what you would get if you went through and added these together. So this is the function that represents the addition of these two things. I want you to make your best effort at exercise 5 and ask you to do the difference function. And I'll just give you a little heads up. Always be careful subtracting. Okay, there's something you got to do with your signs. Hint, hint. So g minus f of x is going to be g of x minus f of x. Notice I put the functions in a different order than previously just to make sure you're still awake. Okay, so the function g is coming first this time. So g of x is 2x minus 7. Here's the thing to remember. Okay, this minus sign needs to be distributed to the whole function that comes after. So what I like to do to make sure that I do that, I don't trust myself to do that in my head. So I'm just going to put a parenthesis here so that I remember I need to distribute that negative, that minus sign. And then f of x is x squared plus 5x. So when I distribute negative x squared, negative 5x, and then I'm just going to make this look a little cleaner. In algebra, we like to put our polynomials in descending order, although I wouldn't mark you wrong for that. It's a preference, but I am going to collect the like terms. That is a necessity. So I'm going to put my negative x squared first, and then 2x minus 5x is negative 3x, and then minus 7, and there we go. There's my function that represents the difference between those original two functions. If you have a question, comment, or concern, please raise your hand and let's talk about it. And if not, flip the page, and I would like you to do exercise 6. And I know some of you are now recollecting your intermediate algebra as you're looking at this, so it's good for us to review. So f times g, the product function here, is just going to be f of x times g of x. So I take my f of x, which is x squared plus 5x, then I multiply it times the g of x, which is 2x minus 7. So I can multiply these. You have the tools in your math toolbox to do this. It's just foiling, first outers, inners, lasts. So I will do that. My firsts give me 2x cubed. My outers give me negative 7x squared. My inners give me plus 10x squared. And we'll combine those like terms in a moment. Maybe you already did it. And then my lasts give me negative 35x. So as I combine these like terms, this new function, this cubic function, which we are not going to graph things of this nature in this class, but when you take pre-calculus, you will, and you'll have an amazing time if that's your math destiny. But this represents the product. If I go for every x value, what is the new x value when I multiply these two functions together? One more, and then we're going to do a couple of the parts of the next example, not all of it, because I think this is fairly straightforward. Question, what's up?
I'm sorry, can you do that problem again? I'm confused on what you multiply.
Okay, so this is two binomials. Okay, so two polynomials. So the way that we multiply binomials, because we have to make sure we multiply all the terms together. This is just the distributive property, but we have this fun acronym that reminds us to multiply all the pairs together. So my firsts, these are the first term in each of the binomials, x squared and 2x. That gives me 2x cubed. My outers, these are the outside terms as I'm looking at it like this. So I multiply those. My inners, these are the terms that are closest together. And then my lasts, the 5x and the -7. And that just reminds me to multiply every pair together. Any other questions? See how easy questions are to ask? It's amazing. All right, the last one. I would like you to, well, I'm going to set this one up because I don't want you to get too, I don't want you to be too stressed about this. I'm going to have you do the quotient of the next one. So the last one is the quotient function. It is f divided by g of x. And I also ask you to please give me the domain of this quotient function. So f divided by g of x. Okay, so like we saw before when we were considering particular values, I'm just going to do f of x in the top, g of x in the bottom. Well, this is lovely. There's not a whole lot of work to do here. With the quotient function, your work is mainly going to be with the domain. F of x is x squared plus 5x. G of x is 2x minus 7. Voila, I'm done. Nothing else to do there. But I do have to make sure that I address this issue of the domain. There is a value that would be bad, okay, because there's a, notice the domain of f of x is -infinity to infinity. It's a squared function. G of x is -infinity to infinity. It's just a line. But when I compose the, when I create the quotient, there is now something that I have to omit. And so the way you figure it out is you say, okay, I'm concerned about any value of x that would make the denominator 0. So I'm just going to come up here, and for my domain question, I'm going to say, okay, 2x minus 7, that can't be 0. Add the 7, so 2x can't be 7. Divide by 2, x can't be 7 over 2. That's the value I have to omit. So let's write this in interval notation. So basically, my domains started out as -infinity to infinity, but now I have to skip over this value. I believe we talked about this, but it never hurts to see it again. So here's my -infinity, here's my infinity. How do I notate that I'm skipping over the value 7/2? What do I have to do? We're going to do a union. Sure, we're going to do 2 intervals. Okay, because skipping over 7/2 breaks my number line into 2 parts. What's the part on the left? -infinity up to what? There you go. And I'm going to put a parenthesis there because I'm excluding. You don't put a bracket. A bracket means equals, and you've just defeated the purpose of breaking this up. Okay, so a parenthesis here. Now I'm skipping it over. I have to take the whole car off the road, and I have to put it on a new road now. And where does the next interval start? 7/2 and goes to infinity, but again, I put a parenthesis there, and there's my gap in the number line. Okay, all values as close as you can possibly get to 7/2, but not 7/2. That's the only one you have to leave out. Yeah.
So the domain for every other function except the division is infinity, -infinity to infinity?
Of our basic functions, there's only one basic function that has a limitation of its domain so far. Does anyone remember which of the 6 basic functions has a limited domain? The square root. Okay, the square root starts at 0, goes to infinity. But right, so that's why we started with these functions, is because there's not a whole lot of those sorts of details. When we come back in Unit 4, we're going to add a couple new basic functions, and they're going to be a little more interesting. If I said, give me the domain of this, Negative infinity to infinity. There's nothing I can't plug in and square it. There's no value that I can't multiply by 5. Mainly though, we're going to, if I ask you domain and range right now, the thing we've done that for is not necessarily things that look like this. This is going to be a little more in the next unit, but the transformations. What do those transformations do to the domain? So remember the domain and the range of your basic functions. Okay, like for the parabola, domain is negative infinity to infinity, and the range is 0 to infinity. But you get that from the graph. And then the transformations, they take the domain and the range and do things to them. All right, so what I would like you to do, please, is in the next bit, I want you to do exercise 8. The reason I want you to do this is I just want you to see what happens with the addition function when there maybe isn't anything you can do, like terms or combining anything. So do exercise 8 with these 2 new functions. All right, here goes. Don't stress too much. If you're still working, you're probably overthinking this problem. So, but that's my purpose here. So you haven't done anything wrong. So here we go. F of x is the absolute value of x plus 9. G of x is 5x minus 8. This is an absolute value, so I can't just bring things into the absolute value. I can't just bring the 9 out. You're done. There's no like terms. There's nothing else to do at this point. Okay, the only way you could do more is if you were given a particular value and said, what is f plus g at 6? Then you could plug 6 in, but there's nothing else to do here. For that same reason, just because I want to make sure I address it, do problem 10 right below it, f times g of x. Again, I want to intervene here in case you are tempted to overthink this problem. So f of x is absolute value of x plus 9. G of x is 5x minus 8, which I'm going to put in some parentheses because of order of operations, and you're done. Again, you can't FOIL these because these are an absolute value. Absolute value takes precedent over multiplication, so you leave it. Mr. Perkins, what about if I left the parentheses off? Well, that's wrong. Okay, I know you know what you're doing, but you haven't notated it because now order of operations, what would I do first here? What change has been made in the order of operations without the parentheses? This says what's being multiplied by the x plus 9? Just the 5x, not the whole thing. But this says we want to multiply the whole things together. So that's why the parentheses are necessary on this problem, is to say that I am multiplying the whole 5x minus 8 times the absolute value, not just the 5x. Yeah?
So anytime there's an absolute value, you don't solve anything, just write it.
There is nothing that I can do to make this any simpler. So there's nothing else for me to do. Yeah. What's up? You sure can. It's kind of redundant, but it's not wrong. Okay, so if you feel more secure and said, okay, I want to put some parentheses around that too, that's totally groovy, which is not really a word we use anymore, but I just did. Any other questions? You guys are doing great. Thanks for staying awake. All right, the last one I want you to do, and then we're going to finish up this page, and this will finish up the 4 basic operations, and then we'll turn the rest of our time to the 5th operation. I would like you to do exercise 11. form the quotient function, and then determine the domain of the quotient function. Again, most of your time should not be spent forming a quotient function. That should be a pretty quick thing. You should be looking at the domain. That's going to occupy a little bit more of your time. Here goes. So the quotient function is just the quotient of the two functions. So I'm going to put f of x in the top. F of x is the absolute value of x plus 9. G of x in the bottom. G of x is 5x minus 8. If you got that, you did fantastic. That is the quotient function. The second part to the question is now, what's the domain of this? So this impacts the domain. Again, if you think about your basic graphs, absolute value, negative infinity to infinity. It's just the v. 5x minus 8 is a line, negative infinity to infinity. But when I form the quotient, now I have something to avoid. And so hopefully what you said is, okay, in the issue of the domain, when is 5x minus 8? That can't be 0. I've got to avoid the input that would give me an output in the denominator of 0. So I add the 8. I divide by 5. And you have to avoid the value 8/5. So I will do that, negative infinity, then I go up to 8/5, and I put a parenthesis, union. Union is important. Remember, when we are talking about the domain, we're talking about one set of values. That's why we use a union here. We don't do that for increasing and decreasing and constant, and we don't do that for continuity. Okay, those are different things. And so now we have 8/5 to infinity, and there's my domain. I'm going to share the screen so that when you watch the video later, you will be able to continue to follow along and not just hear my voice. The last thing we're going to do, this is no different than anything we've done. We're just now, instead of having an equation to get the values, I'm giving you graphs to get the values. So for instance, I'm going to help you with the first one on exercise 12, and then I'm going to let you roll with the other 3, and that's going to take us to the halfway point today. So f plus g of 2, notice on my graph, the absolute value graph that's been translated is f of x. The line is g of x. Those define the values. I just picked nice, simple graphs. There shouldn't be anything that there's a question on what the output is. I'm not trying to trick you. I won't try to trick you on the test. It should be nice and pretty clear. So here we go. I'm going to use my definition that f plus g of 2 is just f of 2 plus g of 2. And now I'm going to use the graph to determine the values. So the function f at 2. Anybody want to throw out there what you think the output is for the function f at 2? Okay, here's the x value 2, right where I've made that mark. And the y value for f is 1, 2, 3, 4. Yes, whoever said 4, amazing. Thank you for your help. And then for g, what's the value of g at the x value 2? Okay, so 1, 2, 3, 4, 5, 6. That's excellent counting. And then when I add those up, the sum function or the addition function, f plus g of 2 is negative 2. So just take a minute or so and do the same thing for the other 3 problems. Subtraction, multiplication, division. All right, I'm going to get started. Check your work with my work. The first one says, what is g minus f of negative 1? So I'm going to take g of negative 1 minus f of negative 1. So I'm just looking at the graph for these values. So g of negative 1, here is the x value negative 1. G is negative 3 minus f at negative 1 is positive 1. So negative 3 minus 1 is negative 4. F times g of negative 6, so that's going to be f at negative 6 times g at negative 6. So here is the value negative 6 way on the left. So the function value f at negative 6 is 1, 2, 3, 4. G of negative 6 is 1, 2. And so what we get when we multiply those is 8. Are we doing all right? Are you seeing where I'm getting these values from? Last but not least, the quotient function. So I have g of 1 divided by f of 1. So here is the value 1. So g of 1 is 1, 2, 3, 4, 5 down, so negative 5. F of 1 is 1, 2, 3 up, so negative 5/3, and that completes the question. Doing the same thing we did at the beginning of the first page, now we're just getting the values from the graph. So that wraps up the first 4 of the 5 of our function operations. Now we are going to do the last one, and we're going to spend, okay, there we go. We're going to spend the remainder of our time on this one because this is probably new. Probably most of you have not seen, unless you've had some sort of college algebra class before in high school or something like that. The last operation is called function composition. Has a lot of impact on things that we will talk about coming up in the future in this class. So the composition of functions. Okay? If f and g are functions, then the composition of f and g is given by this. So I'm just telling you the notation. Okay, so this is the notation. F composed with, that's a circle, it's not a dot, it's not a multiplication dot. Okay, it's just like a little O. F composed with g of x. Okay, so this is the symbol for function composition. What you say is, if you're speaking this, if you're telling your best friend about what you learned in class today, because why wouldn't you, then you would say F composed with G. Now, order matters. If we had G first, and then the circle and F, we would say G composed with F. Okay, so the order matters in these. It's not like multiplication where the order doesn't matter. Here's a slightly easier way to think about function composition, okay? It kind of goes along with the notation that we already have built up. And so this is always my first step whenever I do any sort of function composition problem, is to do this next thing. So maybe you're asked to do f composed with g of a value or of x, whatever. First step, I say, okay, I'm going to have my function f. And then I'm going to put parentheses for function notation, just like we would for anything else. And what function composition means is I am taking this function g of x, and I'm actually plugging it into the function f. So I'm plugging g of x into f of x. Another way to think about it is, if I give you a value x, and you plug it into g of x, what's happening is you are then taking the output from g of x, and it becomes the new input for f of x. Some books refer to this as nesting functions because you can see you've got one inside the other. Okay, so again, you're looking at this, you might think, oh, wow, this is wacky, and it kind of is. And that's why we're going to practice it a whole bunch. So my first example says, all right, we've got f of x is equal to 2x plus 5, and g of x is equal to x squared. First, we're going to, like we did with adding and subtracting and multiplying and dividing, we're going to do this for particular values. So the first thing I'm going to do is f composed with g of 3. Y'all caught up with me? Because this is important. I don't want to rush through. What's wrong? Okay, you got to stop me. You got to tell me what. You can't just sit there. What's up?
I mean, you can just run that back, but like slower, like I don't know.
Which part slower? This is the notation for function composition. I'm about to show you what function composition is. So I haven't actually showed you anything yet except for notation. And so when you see this dot, this is referring to our fifth operation on functions. It's called function composition. You can see in example, example 3, what my computer uses for the little dot. Okay, so this means my fifth operation, which you have no idea because it's not one of the 4 basic operations you learned in arithmetic when you were in elementary school. So this is the definition for what composition is. Notice my order. My F comes before my G, so when I go over here to show you what this is in notation that you've seen before, the F comes before the G. And what function composition means is I take the function F and I am literally plugging in the function G into it, into the variable, whatever it is. So I then said that this is called function composition, and we say F composed with G. Yes? Let's do the example. You guys are having great questions because I understand why this is confusing and I understand what the notation looks like. We haven't done one yet. So let's go through this and maybe it'll help. And if it doesn't, let's revisit that. Okay? So here we go. We're going to do F composed with G of 5. This, again, is my new notation composed with. But again, we're not thinking like that. So what I advise you to do first, this is what I do first. I would not do the problem in this notation. Is I would say, okay, I've got my function F. That's the first one. And in parentheses, I'm going to plug G of 3. Now, this is a specific value. We're starting with specific values because it's a little easier to see this way. And then, like we did before, we're going to then go into generalities. Okay, well, when I take the value 3 and I plug it into the function G, what do I get when I plug 3 into the function G? Okay. 3 squared is 9. Everybody with me? Okay. So what happens now? I'm not multiplying, Deanna. Okay, this is not symbolism for multiplying. This is function notation. Okay, so I understand that question. That's why I wanted to do the example to address that. So you just told me that the function G evaluated 3. 3 squared is 9. So now what happens is instead of G of 3, instead of that, I put a 9 there. The output of the function G, the output of this now becomes the input in the function F. We're working our way out by doing function notation. So now I'm going to take the 9. Where am I going to plug the 9 in? Into F. 2 times 9 is 18. Plus 5 is 23. So you're doing one function at a time. I evaluated the function G at 3. I did that. I get rid of the G. I no longer have it. We have done that. And then I have 9 as the output. And then I plug that into the next function. A little better? Little better? Little better? Okay, well, I'll come up there while you're doing this next problem. And I'm going to watch you do this. So here's what I want you to do, please, is exercise 13. Do F composed with G of -2. When you're plugging in a value, the final answer will be one number. Yes, you're totally correct. Okay, so what are we going to do first? No, you're right here, and we're going to send some functions. Okay, that's lovely. And now, evaluate the first one. Evaluate this right here. No, we're not multiplying. Function notation says I'm going to take this value and I'm going to plug it into this function right here. So what do you get when you plug -2 into this function right here? Okay, so write a 4 there. Parentheses around it. figured out the value for this. So instead of having that there, you substitute this value. And now we're going to do the next one. What's f at 4? Perfect. And just go ahead and do the rest. Great job. All right, here goes. First thing you should do, this is the symbolism for composition, but we're not to where we can think of it like that, so I'm going to write f with g of -2 plugged in. And now we just work our way outward. What do I get when I plug -2 into the function g? What does this that I'm underlining, what does that become? Okay. G, when I plug -2 in here, -2 times -2 is 4. I no longer need the g of -2. We have evaluated that. That goes away, and it becomes 4. Now what do I do with the 4? It goes into f. That's the next function. So f of 4 becomes 2 times 4 is 8, plus 5 is 13. All right, we're going to keep practicing, but here's what I want you to do. This is the next step of learning. Okay, I want you, on the next one, exercise 14, you're doing function composition again, but this time I've changed the order of the functions to see if you can reproduce in this new situation. So in 14, you're doing g composed with f of -2. So flip the functions around. First step, again, just trying to remind you, none of our brains work with this because this is just the symbolism. Now we're going to do the operation. So here we go. Notice the order of the functions is different. We've reversed them. So now it's g is on the outside because it comes first. And then in my parentheses, what am I plugging into the function g? F of -2. Whatever this value turns out to be, that's what I'm going to plug into the function g. So let's do that. What is f evaluated at -2? What do we get when we plug -2 into this? 2 times -2 is -4, plus 5 is 1. Exactly, that's what you told me. So I've evaluated f of -2. I no longer need that written there. That's the same thing as 1. And so now what remains is, okay, that output becomes the input for the function g. And what do I get when I plug 1 into the function g? 1 squared is equal to 1. Yes, that's the output. So we're using, hopefully it's getting a little looser, we're using our function notation. We're just doing it twice now, okay? Instead of plugging in a number and doing it one time. We're going to switch up the functions. So we're going to go down. I would like you to do exercise 15. 15 defines 2 new functions. The process is the same. I just wanted to make it a little more interesting. So evaluate f composed with g of -2. I'm going to get started, and I'm going to convert my composition notation into our function notation. So the f comes first, so f comes first over here. So this means I'm taking the function f and I'm plugging in g of -2. Okay, so this is always the first step. This hopefully is something that function notation, if I just gave you this on the test, I'm hoping you could do g of -2. So now we're just using it twice. So here we go, g of -2. What do I get when I plug in -2? Did I give you a bad problem? Yes, good job, Trickster. You're awesome. All right, so sorry about that. Accidents happen, I guess. Let's go to the next one. I really apologize. Did not mean to give you a weird problem. Exercise 16. I did not mean to give, so I'll change the value. That was a typo. Do 16. All right, so this time I reversed the order. We've got g composed with f, so g comes first. And inside g, I'm plugging f evaluated at 1. So now, f evaluated at 1, what do I get when I plug 1 into the function f? Okay, when I plug 1 into f, 5 times 1 is 5. And then -4, is it -4 or is it plus? You guys got it right. You guys know way better than me. Thank you for being awake. And so that is g of 5 times 1 is 5 plus 4 is 9. And then g of 9, when I plug 9 into g, what's 9 plus 1 is, and then that's just going to stay square root of 10. That's a lovely value. The previous one was a square root of -1. We haven't talked about complex numbers yet. That comes up a little later. So what I want you to do then is we're going to go back to exercise 15, and I just want you to do f composed with g of 3. A nice, that's a terrible 3, a nice relaxing value to do that problem with. All right, so f composed with g, the f came first, so we've got that on the outside, and then the g of 3 goes on the inside. And so when you plug 3 into the function g, what do you get? 3 plus 1, when I put 3 into the function g, 3 plus 1 is 4, and then the square root of 4 is 2, indeed, thank you. And then when I plug 2 into the function f, I've got 5 times 2 is 10, plus 4 is 14. Are we doing a little better? Excellent. That makes me super happy. Is anyone having any concerns? Okay, so what we're going to do, we've got 20 minutes, we've got plenty of time. Our next couple of examples are going to be just like we did with the other 4. Okay, now what happens if I'm not concerned about a particular value? What if I just want to know what the new function looks like? And then we're going to finish off by then doing this same thing, but getting the values from graphs or tables. Okay, so that's how we're going to roll. And then if there's time left, I'll answer homework questions, or if you need a little more insight about function composition, then all that is good. Actually, I just erased the functions we're about to use, but I can rewrite them. So we're going to use these same 2 functions, f of x is 5x plus 4, and then g of x is the square root of x plus 1. And this time, instead of having a particular value, in example 4, I ask you, what is f composed with g of x? Okay, what is the general form of the function? So we're going to do the same first step that we just did. Okay, I'm going to take my function f, that comes first. You always put the first one on the outside. And then inside the parentheses, what am I going to put now? G of x, okay, just the general function g of x. Now there's no arithmetic to do here. What am I now going to substitute right here for what I'm underlining? G of x. What is g of x? It is the square root of x plus 1. You with me? So now what this is saying, and I know it's a little goofy, but what this is saying is now in the function f, everywhere there's a variable, you are going to put square root of x plus 1. Now, to make this a little easier, because I know sometimes you're plugging something with an x into something else with an x, and it seems a little weird, what I'm going to recommend you do is this. First thing I'm going to do is I'm going to go and write the function f without any x's. I'm just going to leave spaces. Okay, so function f is 5x plus 4, so I'm going to write 5. I'm going to put a space plus 4. So instead of an x, I just left a gap there with some parentheses. What am I going to put in these parentheses? What are we substituting into the function f? There you go, square root of x plus 1. That's it. There's nothing to be simplified on this problem. You can get rid of the parentheses if you want. You can have 5 times the square root of x plus 1, but you can't distribute. There's no like terms. There's nothing else to do. So congratulations, you're done with that problem. So here's what I would like you to do, which is the next problem right next to it, exercise 17. I want you to flip it around. I want to know, okay, this is f composed with g of x. Then what does g composed with f of x look like? What happens when I substitute in the reverse order? All right, this time g comes first. So the g is on the outside. And into the parentheses, I'm plugging in f of x. So here goes. What am I throwing into the function g? What goes inside those parentheses now? 5x plus 4. Okay, we reverse the order. So far, so good? Anybody got a concern? Okay, so now in the function g, everywhere there's a variable, I'm going to plug in 5x plus 4. So again, so that I avoid confusion with all these x's, because I don't want you to think we're multiplying, the x times this thing, I'm substituting. So what I'm going to do is I'm going to take my function g, the square root of x plus 1, and I'm going to go to square root of my gap plus 1. Okay, I just put parentheses. Anywhere there's an x. My brain is confused, so this helps me keep everything straight. Now in these parentheses, I am just going to plug in 5x plus 4. There is one little thing that I can do on this particular problem. I do have a like term that I can combine. So this becomes the square root of 5x plus 5, yes. The reason we can combine those and we couldn't before we can combine these because they are both underneath the radical. So they are legitimate like terms. Here, this 1 is under the radical, this 4 is outside. You can't combine those. If you have a question, ask it. If you feel like you're ready, exercise 18. I change up the functions. We got 2 new ones, and I would like you to do f composed with g of x. All right, so f composed with g of x. The f is first, it's on the outside, so what I'm plugging in is the g of x. So g of x is equal to x squared minus 2, if I've written that down right. Is that right? Okay, thank you. And now I'm going to take the x squared minus 2, I'm going to plug it into the function f. Here's the function f, it's just x plus 3. So this is x, my space, plus 3. So into that space, I'm going to put x squared minus 2. Okay, this is addition, it's not multiplication, I'm not distributing, so I just have a like term. So I have x squared, then negative 2 plus 3 is plus 1. All right, our last general example is if you would then, with those same two functions, the last one on page 3 of the handout I gave you, reverse the order. G composed with f. And there is a little bit of an algebra. You got a little bit of multiplying to do on this one, just to bring back some happy intermediate algebra memories for you. All right, so G composed with F, the G comes first, the G is on the outside, and inside I'm plugging in f of x. And so in this case, f of x is x plus 3. So I'll plug that in right there. And now everywhere I have an x in the function G, I'm going to leave a space so that I can plug that in. So the function G is x squared, so something squared minus 2. And inside that something squared, I'm going to put x plus 3. Now remember, with our squaring, we can't just square individual terms. You've got to do some foiling. So you, hopefully on the side of your page, you wrote x plus 3 times x plus 3. And what that gets me is x squared plus 6x plus 9. You don't know where that came from. If it's been a long time since intermediate algebra, come up after class. I got some videos that I can send you where I do some foiling, okay, just to remind you real quick. Okay, but we're running out of time, so I don't have time to go through and foil the whole thing right now. So x squared plus 6x plus 9, and then minus 2 gives me x squared plus 6x plus 7. And that is the composed function. All right, we are going to finish up by going to the last page. We are going to do the same sort of thing we started off with our composition. The only difference now is in the last 10 minutes or so that we have, we're just going to be reading the values from the graphs instead of being given functions. So for instance, I'm going to look at graph 2, which you can see right there. And what we're going to do is using graph 2, we are going to find, we're going to do this one together, f composed with g of 2. All right, so again, same first step. I'm going to do f composed with g of 2. So the f comes first, it's on the outside. Oh, hey everybody, sorry. I'm having a great time up here, but you can't see a thing. Sorry, it'll come on in a minute. Thanks for letting me know, because I really didn't know. It's amazing you all can learn anything. Here we go. Yay. Okay, so what I wrote while you couldn't see it is down here, f composed with g of 2. I just converted the notation. So the f is on the outside, and then we've got g of 2. We all caught up? Yes. All right, thank you. I need as much help as I can possibly get. So we're going to do the same thing. I'm going to go to the graph. I'm going to appeal to that, and I'm going to ask, what is g evaluated at 2? We're just doing one thing at a time. So G is the wavy graph up above. And when I go to the x value 2, what's the value of G at the x value 2? Okay, -2. This is it right here where my pen is. So I'm going to plug now a -2 into my parentheses. Again, this is the same thing we were doing before, just with a graph. So if this is hitting you a little different, just let me know. And now I'm going to take f and I'm going to evaluate f at that new value, -2. So what's f evaluated at -2? Okay, f is the line. Here is -2. And when I count 1, 2, 3, 4 down, f at -2 is -4. Please do the same thing for the problem right below it. What is G composed with f of 4? If the G comes first, it's on the outside. And then on the inside of the parentheses, I've got f of 4. So here goes f of 4, my line. What is the line evaluated at the x value 4? What y value pops out of that? Okay, here's the x value 4, just made a little mark. Up 1, 2. In fact, both functions have the same, that's just coincidence. But the one I'm concerned about is the line. The y value is 2. Now I go through, what's the value of the function g, the curvy function, the wavy one? What's the value of that at the x value 2? -2. We just saw that a moment ago. There it goes. I'm just going to pick and choose a few other problems because we got about 5 minutes left, and I just want to make sure I address everything that I intend to. The next thing I'd like to address is the one right below it, where I've got the function composition, but I'm using the same function and I'm composing it with itself. That's a legal math maneuver, no problem. Just use the same notation we just did and go the same process. Evaluate the function on the inside and then put that new value on the function on the outside. Give it a try. It's your best effort. G composed with G of 0. So G composed with G, the G comes first, so it's on the outside, but then it also comes second, so I've got the G of 0 on the inside. So the first thing I'm evaluating is the G of 0 that I just underlined. And what is the graph G, the wavy graph? What do you get when you evaluate it at 0? 2. Okay, right here, here's 0, you go up 2, there it is. So I'm going to take that G of 0 and I'm plugging it in right here, 2. And now we're just doing the same thing we did before, but now instead of using the function f, we're using the function g again. So what is now the function g evaluated at 2? So what do we get? -2. That's the third time that's occurred in our problems. Go to the next one that's on the right. I would like you to do the middle problem, g composed with f of -1. I have a particular reason. That's why we're skipping the other two, just time's sake. G composed with f of -1. I don't want you to stress. I see a bunch of you looking at me, and that means you're doing the exact right thing. So I've got the g on the outside, so the g comes first, and then on the inside I've got f of -1. So then you go up to the graph. What is the function value at f? It looks like a square root function. What's the value of that at -1? There isn't one. Perfect. You noticed what I needed you to notice. So this is undefined. The function f is not defined at the x value -1. The graph doesn't exist there. So you're done. You stop there. Okay. With our final, we're going to do two more. Same thing we already did. The only difference here is now we're getting our values from a table instead of getting it from a graph or an equation. So let's do the first one, f composed with g of 3. The top table represents the relationship for f. The bottom table represents the relationship for g. Okay, so you're going to use both tables for f composed with g of 3. All right, so f composed with g of 3, the f comes first, so it's on the outside, the g comes second, so g of 3 is on the inside. So when I go to the table that represents the relationship for the function g, what is the output for g of 3? Okay, it's right here. When I plug in the x value 3, I get the y value -2 out. And now I'm going to go to the table that represents the relationship for the function f. And what is f at -2? Okay, it's right here at the top, and so that is 1. So last problem for the day, if you would reverse it and do the next one, g composed with f of -2. And then before you pack up, I just have a couple things I want to mention to you, and then you're out of here. All right, the g comes first, so I put it on the outside. On the inside, I have f of -2. So we just did f of -2. That is on the top one, and I've already marked by it. When I plug in -2 into f, I get 1 out. And then when I plug 1 into g, I get 2 as the output. Okay, so let me stop sharing the screen, and then let me stop recording.